Okay, so last we talked about the cursified dimensions, and I mentioned the curious fact that the volume of a sphere of radius 1 is going to go to 0 as the dimensions number of dimensions go to infinity. And I explained why by bounding it by the density. Okay, so and the density was the density of the Gaussian variables were these the number of dimensions. So let's see at this code snippet that tries to highlight the behavior that I talked about last time. Okay, so what I'm going to do now, I'm going to run like a Monte Carlo simulation that will estimate the volume of a sphere of radius 1 with increasing a number of dimensions. So number of dimension will run from b equals 1 to max number of dimension, which is 20. Okay, and if you remember, a Monte Carlo simulation would randomly choose points, and then basically think about taking the sphere and bounding it by a cube, and then I'm randomly picking up points in the cube and count how many of them are in the sphere. That's Monte Carlo. I'll do something very similar. I'll randomly sample points from a random vector, a Gaussian random vector, and see how many of them happen to fall in the unit circle. And I'll do it for increasing number of increasing dimensions, and see if I get the behavior I expected, that the volume is going. So the estimate of the volume is going to be simply the number of points that happen to fall inside the circle or the sphere, and the number of points I drawn overall. That's Monte Carlo. It's so simple, but just some statisticians said, that the appearance of Monte Carlo techniques gave them the feeling of freedom, because things that were very, very hard to do in statistics becomes really nice and easy with Monte Carlo. So that's the way we estimate the volume. Very simple. And now let's go look at the code specifically. So we said that the maximum dimension we're going to try is 20, and the number of samples. Well, in Monte Carlo, the more the merrier, which means the more samples you draw, the more precise you get your estimate of in our case, of the volume. So I started like with 100 and then increased it to a bigger number just to see more accurate results. Now I have pi to be 3.14. You could be more fancy and get a more accurate estimate. Now I'm starting to increase the dimension, and for each dimension, I do the following exercise for each dimension. I create a random vector of Gaussians with average 0 and standard deviation 1/2 pi. And the random vector is of dimension d, depending on, I'm increasing d. And then the next thing that I do is I calculate the distance. So for each element in the vector, I get the square of that, and then I see if it's less than 1. And that's basically at line 30, I'm checking inside the circle or inside the sphere, dimension d. And if it's inside, then I increase the count of the number that were inside by 1. And I keep going and, increase the d. Now, once I am done with the simulation, I write the volume. So the volume is the number that are in the circle over the number of samples. Okay, so that's the simulation, and see the result. So for d that we're starting with the line, and then the circle, and then the sphere, and then 4 dimension, and 5 dimension, 6 dimension, 7 dimension, and so on. You see that in the beginning, the volume, there's a good chance that you land in the inside. But as you increase the dimension, quickly you run away from that, and you see that here you're not falling in this circle, basically. So you're converging to 0 as previously we've calculated that that is what we expected. We see intuitively how it happens in a simulation, a Monte Carlo simulation. So any questions or comment on this?
Can you perhaps give an intuition of the same topic, the curse of dimensionality, from other fields or problems?
Maybe not from other fields, but from something you're familiar with. Okay, so if you're trying to do an attack on a machine learning model, if the machine learning model feature space is a geometry with high dimensions, then it will be hard for you to fool the machine learning model to think that a point, a sphere around the point looks in some way. So any attack that is related to K and N basically will fail in high dimension.
Okay,
another way to think about it is that essentially what is happening is that think about a picture think about a square. It's not a real picture because the square is low dimension, but think about a square and think about points that are being pushed to the surface of the square. So they don't, it's like the points are pushed to the surface of the square. They're not in the center because you have many directions. It's just an intuition. It's not, okay. Did I answer your question?
Yes, thank you.
Welcome. We see these type of things in science in other cases like relativity or quantum theory. There are things we don't have experience. So if you look at all the traditional approaches to machine learning, they were very much and like the observation about the Bayes rule and so on, very much focused on just a few features, or not a big number of features, and then the intuition that we have about geometry still holds. Now, what is happening here is that you have too many directions. It doesn't make sense that all of these directions will be occupied in some sense. So things that are based on getting a feeling what is happening in all of the directions are kind of break because you have too many of them. You see. So it doesn't make sense that you'll have information in all directions. It's the phenomena of well, if I assume that the speed of light is constant, then the length is something relative. That the length of an object is something relative that will have different length by different observers. It's not intuitive. It's because we have no intuition for that. We have no intuition for so many, 10 of thousands of attributes. And that's one of the key challenges that we have in data science and machine learning. Make sense?
Yes.
Okay, great. Okay, any other questions or comments? Okay, so we'll continue next week then. Thank you very much for joining today.
Thanks.
Thank you, Eitan.
Yep. Thanks, Eitan.
Bye-bye.
Bye.